All right, let's get started. Hello, everybody. Thank you for joining us today and welcome to the Astro 3D ECR Astronomers in Australia seminar series. My name is Dorota Bayer and I am an Astro 3D postdoc at the Swinburne University of Technology in Melbourne. Before we begin, we must acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. So both me and our second speaker, Gravinder, are speaking to you today from the land of the Wurundjeri people of the Kulin Nation. And our first speaker, Tania Barone, is speaking to you from the land of the Ngunnawal people. We pay our respect to the elders past and present and extend that respect to all First Peoples joining us here today. So why are we here? This series is facilitated by Astro 3D, the Australian Research Council Centre of Excellence for all-sky astrophysics in 3 dimensions. COVID-19 has affected our ability to travel and present at international seminars this year, especially for us in Australia at 3 in the morning. And this lack of opportunity to network could disadvantage junior astronomers when entering the job market. And this series aims to combat these issues by providing a platform for junior Australian astronomers to present their work to the world. So a little bit of housekeeping. There will be 2 talks over the next hour. Each will be 20 minutes with 5 minutes for questions at the end to give speakers a 5-minute warning. Please save your questions until the end of each talk, but feel free to use the chat function for questions if you prefer. These talks are also being recorded and will be placed afterwards on Astro 3D YouTube channel for educational and scientific purposes. Finally, by being here today, you agree to abide by Astro 3D's code of conduct. Okay, on to the first speaker. Our first speaker is Tania Barone, who is still a PhD student at the Australian National University and the University of SAMI Galaxy Survey. So Tania, the screen is yours.
Great, thanks. Okay, so everyone can hopefully see my slides. So I'll be talking about the last project of my PhD. So this is looking at galaxy stellar population, so integrated global stellar population properties and how they vary in the galaxy mass size plane over a look back time of 7 gigayears. So this is building on my earlier PhD work looking at low redshift, and now we're extending that work to intermediate redshifts using the LEGA-C Survey. So firstly, why are we looking at stellar populations? So galaxy evolution is influenced by a huge range of internal and external processes. Many of these interrelate, so processes determined by the environment, so interaction with neighbours, mergers, gas removal from infall into a group or cluster. And then there are these internal processes such as star formation and AGM feedback, which are more determined by the local properties of the galaxy. And as I said, a lot of these interrelate, and given the very sort of stochastic nature of these processes and enormous timescales, it's impossible to know the exact combination of processes which have acted over any particular galaxy's history to lead to how we see it today. But what we can do is we can look at the current stellar population, because the current stellar population is like a fossil record of the galaxy's star formation and assembly history. And so by looking at large statistical trends between stellar population parameters and other galaxy parameters, we can start to link together the galaxy structure and its stellar populations in order to understand, or in order to resolve, which processes are dominating galaxies' evolution and leading to how we see it today. So this isn't a new idea. Many studies have looked into how stellar population properties correlate with other galaxy properties. So some of the main scaling relations identified are with mass, with environment, velocity dispersion, morphology. All these other secondary correlations have been found as well. But the issue is that, to an extent, with galaxy evolution, we tend to find that everything sort of correlates with everything. And so it's really hard to identify which correlations are due to a causal trend and which are due to another underlying trend. So this is what we're really trying to identify in our work, and has been the main driver and the main theme throughout my thesis research. Is we're trying to identify which correlations are more likely to reflect a causal relation compared to other relations which are due to other underlying trends. So to simplify this, we look at mass and size, because these are very foundational quantities. And so we want to understand how galaxies, how the evolution of a galaxy within the mass size plane, as shown by this schematic from Capillary 2016, how that links with the changes in its stellar population properties. So the age of the stellar population, the age of the stars, their global metallicity, their abundance ratios. And with mass and size, we can also look at correlations with specific structural parameters, notably the gravitational potential, or a proxy for the gravitational potential, and the surface mass density. Because as you'll notice, if we look at these parameters, so mass, potential, and surface density, they only differ by a factor of galaxy size. And so we can use that to understand the relative observational uncertainties in these parameters. And that gives us an indication of the intrinsic scatter in the relations. So we can use the scatter about the relations and what we know about observational uncertainties to figure out which are more intrinsically tighter if we were to observe them without any observational uncertainties. So I'll firstly summarize some low redshift, our earlier low redshift results, and then go into what we predict and what we're doing with our current results, our current project. So we firstly looked at early type galaxies at low redshift and then star forming galaxies. And as I said, we looked at how properties such as age and metallicity in particular, how they correlate in the mass size plane. And interestingly, we found that for both early type and star forming galaxies, we found the same result. We found the same correlations. Notably, that metallicity correlates best with the depth of the gravitational potential, and that age correlates best with surface density. And when I say best, I mean these relations had the lowest intrinsic scatter and the lowest residual trend with size. So most of us will be familiar with the well-studied metallicity mass relation, for example. But we found that metallicity gravitational potential is actually a tighter relation. So the current work is now extending this to intermediate redshift galaxies. So why are we looking at intermediate redshift? What are we trying to test? We're trying to test our hypotheses for what led to these metallicity and age correlations. So I'll very briefly go into what we think is causing these relations, so our hypotheses, and then how we're going to test them using the LEGA-C Survey. So firstly, the metallicity gravitational potential relation. So if we very, very oversimplify the sort of metal enrichment of galaxies, we can think of the metallicity in a galaxy is going to be determined by its stellar mass, because the more stars you have, the more metals you're generating. So the metals you make, but also the metals you retain. So this schematic here really nicely shows how we have star formation and AGN feedback. So we often have gas being expelled from the galaxy, and that may or may not be recycled in again. And so the fact that we find that metallicity correlates very tightly with the potential rather than the mass, which is what determines how many metals you make, we think this is due to the gravitational potential regulating the metals that you retain in the system, because the gravitational potential determines the escape velocity required by supernova and AGN feedback to eject metal-rich gas from the system. And so it's not the metals that you make that determines your stellar metallicity, it's the metals that you retain in the system. And there's a huge body of supporting evidence for this. For example, the decreasing radial gradients within galaxies. So the potential is deeper in the center and more shallow in the outskirts. And galaxies, again, are more metal rich in the center and less in the outskirts. We also, in a adjacent work, we showed that the global gas phase metallicity in star-forming galaxies also correlates with the gravitational potential. So if this is true, we should find this at all redshifts, because this is a causal relation. This should affect all galaxies. Also, so far, I've only explained how this could originate with in situ star formation. But we know from our first project that this relation also exists in early type galaxies. And so we need to understand how this could be maintained in mergers. So we hypothesize that it can be indeed maintained in mergers. And this is supported by some simulations by Bowen, Kolshin and Ma 2007. So what they showed is that the density of a satellite impacts where it accretes onto a host. So low metallicity, very diffuse galaxies are very easily disrupted, and so tend to accrete their low metallicity material at large radii. Conversely, a very compact, high metallicity satellite will survive multiple passes and accrete its high metallicity material into the center of a galaxy. And so we can see how this relation can also be maintained through galaxy mergers. Okay, so this is our hypothesis for the metallicity gravitational potential relation. So these are the two relations I'm really going to focus on in this talk: metallicity and potential, and age and surface density. Okay, so what about age and surface density? So there was discussion that it could be due to compactness-driven quenching mechanisms. But we showed at low redshift that star-forming galaxies also show this correlation between age and surface density. So it must originate before quenching. So the explanation that we settled on was that simply compact galaxies form earlier. And this fits very well with what we know about high redshift galaxies. In the early universe, there was a very high gas fraction, leads to very high star formation rate densities. And this then led to galaxies forming very compactly in their rapid in situ build-up phase. Okay, so now how do we test these hypotheses? So what we're doing is we're going to map the evolution of these scaling relations from our low redshift results, which use the SAMI Galaxy Survey and the SDSS survey, to the intermediate redshifts using LEGA-C. So look at a 6 to 7 year look back time. So here are our two hypotheses. Metallicity potential is driven by the escape velocity of gas. We therefore expect there to be a correlation at intermediate redshifts. There's no reason why there shouldn't be if this is a relation that affects galaxies at an individual level. However, for the age surface density relation, our hypothesis to test is that this relation is built up from galaxies that have formed and evolved larger at later times. Therefore, if we're looking 60 years ago, this relation is likely to be a lot weaker because it hasn't been built up for as long. So these are our two hypotheses. There should be a relation for metallicity, and the age relation we expect to be weaker. Okay, before I dive into results, just an interesting caveat with looking at galaxies across redshift. So when we're looking at galaxies and how they evolve in the mass size plane with redshift, we're seeing the combined effect of two things. Firstly, how individual galaxies evolve. So this is a nice schematic showing how individual galaxies are expected to evolve in morphology, but also the evolution of the population as a whole due to the change in its members. So here is a figure adapted from Van der Velde 2014. So this shows how in the mass size plane, both the star forming and quiescent sequences evolve. And this is due a lot to the fact that at later times, galaxies are added with larger radii. And so we need to keep in mind that there are these two different processes happening. Individual galaxies evolve, but also the population as a whole changes, especially when we're talking about the star forming sequence, because star forming galaxies quench and they leave the sequence. And then as new galaxies merge together and form, we have new galaxies added. So the members of a population is constantly changing. Okay, so let's get into our new and exciting results. So here I'm showing the mass size plane for 3 redshift bins. We've got metallicity in all 3, color mapped by metallicity in all 3 panels. And here we have our low redshift results in SAMI, and then we have the LEGA-C results in 2 redshift bins. And so what this shows is that similarly to our low redshift results, we see that metallicity trends along lines of constant potential, which are these dashed lines. The dotted lines are constant surface density. And so as we hypothesized, metallicity varies in the same way across redshift. So this metallicity potential relation that we found at low redshift also exists at a look-back time of 6-7 gigayears. So, and this really supports our hypothesis that individual galaxies themselves follow this relation, and that this is due to the regulation of metal retention. So this is just, these arrows just show that metallicity varies in the same way.
We have 5 minutes left.
Great, thank you. And here we have mass, size, and age. So once again, mass size planes. Low redshift, intermediate, and then higher redshift. But unlike metallicity, the variation in age changes across redshift. So if we look at the highest redshift bin, age varies along the quiescent sequence. So I'll note as well, these are all quiescent galaxies that we're looking at in this project. So quiescent galaxies. At intermediate redshift, there's no clear age variation. And then at low redshift, as we found earlier, age varies along lines of constant surface density. So these dotted lines here. So the variation, so scaling relations with age change across redshift. So we looked into this a little bit further. Specifically, we looked into how this relates to the slope of the quiescent population itself in the mass size plane. And so what we know from other studies of the mass size plane is that the quiescent sequence has pretty constant slope of 0.5 in the mass size plane. So that's shown by this figure here. But the intercept changes, so galaxies are larger at lower redshift. Now, this is really important because a slope of 0.5 in the mass size plane reflects a constant surface mass density. And so that's what I'm showing here. So we have low redshift and then intermediate redshift from LEGA-C, mass and size. And if we look at instead mass surface density, so we see that the slope of the quiescent sequence is about 0.5. So if we look at surface density, we get these flat sequences. So at all redshifts, all quiescent galaxies tend to have a characteristic surface mass density. So if we put this together with what we know about how individual galaxies evolve in the mass size plane, so we know star-forming galaxies evolve along parallel sequences in the mass size plane, and that at lower redshift, they have a higher, a larger size. So if we convert this now, so take this same information and put it into the mass surface density sequence, mass surface density plane, we find that once again, galaxies build up in mass, but they also build up their surface density as they build up via star formation. And then once they quench, they tend to stay at a fixed surface density. And as we see at higher redshift, galaxies tend to start at a higher surface density, they evolve more compactly, and then they remain more compact compared to low redshift. So putting these two schematics side by side, this is really just taking what we already know about the mass size plane and putting it in terms of mass surface density. And the reason we're doing this is to try to explain why we find a relation between age and surface density at low redshift. Because as you can see, now the age of galaxies is going to correlate with its surface density. So to look at this in another way, this is going to be the mass size sequence the mass size sequences, the star forming and quiescent galaxies at high redshift. At intermediate redshift, it's going to be a little bit lower. And at low redshift, it's lower again. And so when you're looking at this combined effect, you're looking at galaxies at low redshift that have formed and evolved at a range of redshifts. This is what we see. We see this integrated effect where galaxies for both star forming and quiescent galaxies are older when they have a higher surface density. And this is what leads to the age surface density relation at low redshift. And it also explains why we don't see such a strong relation at intermediate redshifts, because it hasn't had enough time to build up. So to summarize, there is a very tight correlation between the metallicity and global stellar metallicity and the gravitational potential at both low and intermediate redshifts. And this reflects a causal relation. The gravitational potential determines the escape velocity for metal-rich gas to be ejected from the system. And then lastly, there's a very strong age surface density relation at low redshift that we found in earlier results. But here I've shown that that doesn't exist at intermediate redshifts. And we believe this is because the relation is built up over time and results from galaxies forming, evolving and quenching at different surface densities depending on redshift. So I'll leave it there and I'll leave up the results summary. Thank you.
Thank you very much, Tania, for this great talk. Do we have any questions from the audience? Please raise your hand or write in the chat.
Yeah, I know it's a very interesting question and also very hard to to tackle because we have to deal with a lot of systematics and the biases. I'm just curious, and because when you deal with the low redshift and high redshift population, do do you find the surface brightness issues becomes a significance, or if you feel that as a significance, how do you deal with that?
Yeah, so when, of course, looking at higher redshift galaxies, we're going to be restricted to only galaxies with much higher surface brightness. And so what we do is we look in we test using a very narrow mass range. So when we compare the intermediate redshift results in LEGA-C to the low redshift results in SAMI, we've tested restricting them to both have the very same mass range to ensure that we're looking sort of at galaxies in the same part of their evolution, and we still find this result. And so we've also had a look at what point are we restricted to only high surface brightness galaxies. So we do ensure that we're not biased by only looking at the very brightest galaxies.
Thank you.
Right. My question is regarding the first part of your talk, the metallicity and gravitational potential relation. I was wondering, given that I'm not sure how how the spatial distribution for the LEGA-C survey is, or if it's measurable, but for SAMI, I definitely know it is measurable. So have you looked at this relation in a more spatial spatially resolved way, in terms of like metallicity profile versus the gravitational potential profile?
Yeah, so I personally haven't. That's something that Francesco De Eugenio, he's been looking into. So looking at the radial trends within galaxies, because as you mentioned, SAMI is excellent for looking at spatially resolved relations and radial gradients. This work we've really focused on global stellar population, so that way we integrate the light over the whole galaxy to get as strong results as possible, because it's to do robust stellar population analysis requires relatively high signal to noise data. And so when you start looking at spatially resolved, you're sort of breaking apart the data that you have. And so in LEGA-C, it can be quite tricky to get high enough signal to noise to look in a spatially resolved way. But I do know that's on the cards for that happening in the LEGA-C team. But yeah, my work has really just focused on global trends.
Great, thanks.